All right, welcome to Statistics Part 2. So we've talked about probability. We've used that to introduce the concept of random variables. Variables that their value depends on probability, depends on randomness. And we started by talking about discrete random variables with a special one for binomials. Now we're going to talk about continuous random variables and a very special continuous random variable that you have seen before, probably somewhere in your life, called the normal model. All right, that's the bell curve. So this is a continuous random variable. We can call it X, just like we call a lot of variables X. And it has some mean mu, standard deviation sigma. And this is how we write it. X is normally distributed with those two parameters. Remember, for binomial distributions, right, we had binomial with n and p. Well, normal distributions, we don't have a number of trials. We don't have a probability of success. We have a mean and standard deviation. So it has different parameters, okay? So the thing, even though there are still two blanks inside this distribution for the parameters, those values, those parameters mean different things. It's not trials and success anymore. It's mean and standard deviation. And any distribution, any special distribution will have different parameters on average. So we'll use these to approximate things that are more or less unimodal, continuous, and symmetric. So one peak, continuous, not discrete, and symmetric. So let's get into an example with this. Let's say we're looking at the mean annual rainfall in Portland. Let's say it's unimodal and approximately symmetric, not perfectly symmetric, but mostly symmetric, with a mean of 40 inches of rain and a standard deviation of 8 inches of rain. And we're rounding to the nearest inch here, okay? Fill in the blanks and then label the normal model for this situation. Okay, technically for rounding to the nearest inch, we have discrete data, but we're just doing that to clean things up. Actual rainfall is continuous data, right? You can have 3 inches of rain, you can have 4 inches of rain, and you can have every number in between. So we're going to say let X be the annual inches. That's not how you spell annual. Annual inches of rainfall in Portland. So we know it's unimodal, continuous, and symmetric here. So a normal model makes sense. We know the mean is 40 inches and the standard deviation is 8 inches. So we're going to kind of write it like this. X is normally distributed with a mean of 40 inches and a standard deviation of 8 inches. So remember when we were looking at binomial distributions? I think I can find this somewhere quickly. Remember when we were looking at binomial distributions, we could see the probabilities of each event. It was just how high is that rectangle? Well, normal distributions are the same. We are seeing the probabilities, just how high each thing is. But the whole thing about continuous is that there's infinitely many possibilities. It's not just 0, 1, 2. It's literally everything in between. So the height of the curve still shows the likelihood, but we're going to calculate probabilities a little differently. That's going to pop up later. So whenever we try to draw pictures for normal distributions, every normal distribution really looks kind of the same. They all look like this, okay? What matters is where is the center and how spread out things are. So the center is the mean, okay? Remember we had the difference between mean and median. Median was the middle and mean was the average. But if something's symmetric, then those are the same things. So 40 inches of rain is just right here. It's in the middle. It's the most likely outcome. That's why this probability curve, right? This is probability. That's why the probability curve is the highest right here at 40. 40 is the most likely. 40 is the average. Are not always the same thing, but they are the same thing here for normal models. And the standard deviation is 8. And so how we kind of graphically look at that is that normal models have this like inflection point right here. Notice how it's kind of like curving. It's like curving down here. Here, let me make it thicker. Curving down here. And now it starts like curving the other way over here, where it changes like the shape of its curve. That's the inflection point, and that's going to be 1 standard deviation above the mean. So 8 above the mean is 48. And then we can keep on adding 8 to get a really good picture of what this looks like. And again, it's symmetric, so we do the exact same thing in the other direction as well. Now we can look at the likelihood of different levels of rainfall. So you can see that in Portland, if you got 16 inches of rain, that would be really rare. Look how unlikely that is, right? It's so close to 0. But like, I don't know, 44 inches of rain, that's a pretty normal event. We'll talk a little bit in this video about what's normal and what's not normal right about now. All right, let's get into the empirical rule. So if we have a normal model, about 68% of the values are going to be within 1 standard deviation of the mean. Okay, so about 68% of the values is within 1 standard deviation of the mean. All right, if this is our mean, and this is 1 standard deviation above the mean, right, at that inflection point, and 1 standard deviation below the mean right here, mu minus sigma, we know 68% of the data should be here. That's called the empirical rule. But wait, there's more. We also know that 95% of the data is within 2 standard deviations of the mean. Again, we know 95% of the data is within this big area. 2 standard deviations above the mean and 2 standard deviations below the mean. And if you think there's more, you'd be right. Because we also know that about 99.7%, which is a lot of percents, is within 3 standard deviations of the mean. So let's see if I can get this in a picture. 3 standard deviations is a lot of data. If you are more than 3 standard deviations above the mean, we got a wacky, irregular situation going on. Really, really crazy. All right. So visually, this is what we have right here. And again, right here, going to be mu plus 3 sigma. Okay. So most of the data is within 1 standard deviation, which makes sense. Standard deviation is the average distance from the mean. We can think about that. And then really most of the, like almost all the data is within 2 standard deviations. And really almost all the data is within 3. So we've labeled the bell curve to show these. And just to give, some rule of thumb terms, if you will, what we have right here is that if you are more than 2 standard deviations away from the mean, that's unusual. That's an outlier. If you're more than 3 standard deviations, that is very rare. All right. That's pretty much an introduction to normal distributions, kind of what we're talking about here. And in the next video, we're going to get some practice using this rule. Good luck.